let's take a look then. So your calculator actually is pretty smart. So if I take a look at x squared, and I'll do like zoom decimal. There's z decimal for you, right? Should we dedicate this lesson to Jack? This one goes out to Jack.
Yes.
All right. So your calculator, you know that it will calculate the derivative at a point. If we're clever, though, we can actually graph the derivative for a bunch of points. So here's what we do. In y2, you're going to type math, and then you're going to go down to 8. All right, math 8. So we're going to actually ask the calculator to graph the derivative of I'm not doing any problem, I'm just doing what I want to talk about. Of what? So we can pick y1, or if you wanted to, you could actually type in x squared. I'm going to do y1. And we would tell the calculator that the variable is x. Now, under normal circumstances, if we wanted the derivative of a point, we'd type in some value, some x value, right? However, if you actually look down to like number 10, it actually tells you a clever way. Instead of just picking one value, we could tell the calculator to plot the derivative for a lot of values of x. So for all x. And I'm going to change the derivative to a dark line, a thick line, so we can tell the difference between the two. And so now if I graph it, there's the function, and it takes a little time. Your calculator's actually thinking. That's a picture of the derivative for every single point. So, for example, if I wanted the slope at 1, well, the derivative would tell me that the slope is what at 1? It's 2. It has a value of 2. So do you see how the dark function or the derivative function is telling us what the value of the derivative is for different x values? Sort of. Let's talk about this a little bit more. Actually, did we?
Wouldn't that be the tangent line?
No, it's actually not the tangent line. It's a graph of the derivative.
That's for all values.
Right. This for all values on this graph. As a matter of fact, here's another good place to start. If you look at the parabola, what would you say the slope is at the very bottom of the parabola? 0. So that means for the x value 0, the derivative 0. Look at the derivative function. Is the derivative function 0 when x is 0? It totally is. What graph are you looking at? Doesn't this tell us that the value is 0 when x is 0? Yeah. I know you were.
Okay.
And that's hard because when we're looking at the dark function, we're not looking at what the slope of the dark, like the bold line is. We're looking at the value, the y value that it tells us. And the y value is actually the same as the derivative. Let me show you one more thing, and then we'll talk about this graph a lot more. David Bellier in the other class was looking at patterns.
Yeah, he told us about this.
And he actually said, guess what? You could do the derivative of x squared. You could do it out by hand. You could do the limit of the difference quotient. But he guessed correctly that the answer is going to be 2x. He saw a pattern there. So if we actually type 2x into our calculator, and I'm going to turn the bubble guy on. Have you ever seen the bubble guy? All right. So here's the where's the bubble guy? Here's the bubble guy. And the bubble guy will go along, and this is actually to see, is in fact the derivative of x squared 2x. Now you could show algebraically, but this is fun because you get to see the bubble guy sort of move along and trace over. So that means that the bubble guy is exactly 2x, and which is exactly the derivative. All right, let's make some noise. Woo! No. Let's make some observations about the derivative and the graph.
Like for our homework, since it's like mainly on the calculator, can we just do it like on the sheet for the ones that like we have to use the calculator?
I don't know if I like this. Let's see. So you're saying for 1, 3, 5 you can do it. For 7, all right, you can probably do that. For 8, 9, and 10. Okay, well, so here's the thing, though. When it asks you to, like, for 8, 9, and 10 to graph the function and its derivative, you're going to need to actually draw that.
Okay.
Wouldn't you want it on the other sheet because you don't have to hit it?
Oh yeah, you're
Like,
right.
if you were telling me that you wanted to do the work you could on the front and any work that you couldn't fit on the back because you wanted to save paper, I'd say that's fine. All right. All right. Whoops, that's not what I wanted.
How'd you highlight the whole screen?
I didn't. All right, so here, make some observations. What can you tell me about all right, fine. What can you tell me about the function from negative infinity to 0? Something's true about the function on that interval. Zach? Decreasing. The function is decreasing. Now, you said something which was great, which was totally wrong. Say it again. Oh, really? That's right. That's not what I thought you were going to say. That's a bummer. Can you just say the first word? Negative. Okay. It sounds funny, but very often students confuse the words negative with decreasing. Betsy actually said the exact right thing. The right connection is when Zach says it's decreasing, Betsy says the slope is negative. As a matter of fact, isn't that exactly what, wouldn't you say that all of the derivative values from negative infinity to 0 are negative? Now, would you agree that all of the derivative values that are changing, like the values aren't always the same, they change, right? But they're always negative. Well, that makes perfect sense, because isn't the slope of the function always changing? And isn't it always negative from negative infinity to 0? Totally. And if we were to look at from 0 to infinity, what would you say about the function, Tali? Great. And that's going to correspond to, what would you say about the derivative, Will? Function's increasing. What's another name for derivative? Slope. So if a function's slope is... Yeah. Isn't that true? Yeah. Isn't this part of the derivative function positive? Yeah. What do we mean by positive? Above the x-axis, right? And right down here at 0, that's where the derivative is 0. I want to show you one more thing, but it's probably a good time. Like, do you want to ask a question? That was a lot to take in, right?
Wait, so decreasing derivative was...
Actually, decreasing derivative tells us nothing right now. It's going to tell us something later. But we don't care if the derivative is decreasing.
When the slope
function.
derivative.
Yeah. The function's decreasing, the derivative's negative.
That sounds like a pretty good statement. When the function's decreasing, the slope, or derivative, is negative.
And when it's increasing, derivative.
Yep. And doesn't that make sense? The statements make sense. Sometimes the pictures confuse us because we forget what positive and negative and increasing and decreasing actually mean. Right? Remember, positive and negative means, is it above or below the x-axis? As a matter of fact, I have a good... What we could... I'm going to change this function to x squared minus 1. And I'm going to get rid of the bubble guy. What is x squared minus 1? What does that do to the function?
Decreases it by 1, so it takes all of it shifts it.
What kind of shift?
A vertical shift.
Vertical shift down 1. So it takes that x squared and shifts it down 1, right? Does that change the slope of the function when we shift it down 1?
It just changes
The position on the graph.
Okay, so just where it is. So it's not going to change the actual slope of the graph. So actually when we go and we take a look, here's the graph shifted down 1. Notice that when we graph the slope didn't change at all. So make sure you understand, can you see that the function is actually negative from -1 to 0? But that doesn't matter. It doesn't matter whether the function is negative. What matters is that the function is decreasing. And from 0 to infinity, the function is still increasing. So the fact that the function's above or below the x-axis has no bearing on what we can say about the derivative or the slope. And just to reiterate, I mean, if I didn't say it clearly the first time, this bold line is like if you asked yourself a million questions, actually an infinite number of questions, and you were to say, okay, here's my function. What's the slope at 0? It's 0. What's the slope at 1? 2. What's the slope at 2? 4. What's the slope at 0.5? 1. What's the slope at 0.7? 1.4. And you kept filling in all these values. Like if you did that algebra, right, for all those values, you would get this line. As a matter of fact, if you knew the function was x squared and you did the limit of the difference quotient, you would get that the derivative rule is 2x, where you'd plug in a value for x to get the slope. All right, so this is just a way to look at it graphically. Here's algebraically, right? Here's graphically. Is it all right? Just the end of the day? Or this is tough stuff? It's okay. All right, fine. All right. We are going to do a lot more with that tomorrow.